On December 16th, the trajectory of interstellar object. 3. Atlas shattered our understanding of orbital mechanics. It didn't just drift. It executed a sudden 33-fold acceleration directly toward Earth. The telemetry suggests its visible anti-tail is not cometary debris, but a directional propulsion system acting as a vector gate. This object is actively evading solar wind and flattening its orbit with calculated precision. We are no longer observing a passive rock, but what appears to be technology establishing a specific approach vector. If you value objective analysis of these anomalies, please take a quick second to like and subscribe. Now, let's examine the physics behind this event. For weeks leading up to mid-December, the interstellar object identified as 3I Atlas had been a model of celestial obedience. Its movement across the vacuum of our solar system was perfectly consistent, adhering strictly to the standard laws of motion. It followed a clean, hyperbolic trajectory, a path defined by the immense gravitational pull of the Sun and the initial velocity with which it entered our neighborhood. In the world of orbital mechanics, this type of curve is the signature of a visitor that does not intend to stay. It enters, swings around the star, and exits, never to return. During this period, the data streaming into planetary defense centers was unremarkable. There was no chaos in the numbers. The object showed no signs of unexpected tail divergence, which would indicate parts of it were breaking off. There was no spin drift, meaning it wasn't tumbling erratically like a dying asteroid. The luminosity, or brightness, remained stable, with no sharp changes that would register as outliers in the daily reports. To the astronomers tracking it, 3I Atlas was steady. In fact, it was almost eerily steady. This is the kind of predictable motion that gives planetary defense teams a sense of quiet comfort. In this field, predictability is synonymous with safety. If you can calculate where an object will be 10 years from now using simple math, it is not a threat. That sense of security evaporated on the morning of December 16th. The shift began at exactly 0412 Universal Coordinated Time. A signal was received from the Mount Lemmon survey, a specialized observatory located high in the Catalina Mountains of Arizona. The message they sent out was not a warning. At that early stage, the data was too subtle to trigger a red alert. Instead, it was a request for confirmation. A digital query sent to other observatories asking if they were seeing the same impossible numbers. The optical systems at Mount Lemmon, which scanned the sky with extreme sensitivity, had detected a deviation in the apparent motion of the comet. In the precise world of astrodynamics, a deviation is a serious matter. It was not just a positional error, which can happen due to atmospheric distortion or sensor noise. It was a registered increase in velocity. The astronomers at Mount Lemmon had been tracking 3I Atlas every night, contributing to a dataset shared by dozens of other observatories across the planet. They knew the object's baseline behavior intimately, but the data spike appearing on their screens at 0412 did not fit the model. In the first few minutes, the immediate assumption was human or technical error. This is the standard procedure in science. When you see something impossible, you first assume your equipment is broken. They checked for calibration issues. They analyzed the local atmospheric turbulence to see if the air over Arizona was bending the light. They checked the charge-coupled device, or CCD plate, in the telescope camera for misalignment. They even ran diagnostics on the software processing the tracking data. Everything came back clean. The telescope was functioning perfectly. The data was real. Within minutes, the query from Arizona was answered. Other stations around the globe had locked onto the same coordinates and were seeing the same thing by 0433 Universal Coordinated Time. 21 minutes after the initial detection, both the Canada-France-Hawaii telescope on Mauna Kea and the Pan-STARRS array had registered a matching anomaly. The data from these independent locations overlaid perfectly. The object had increased its velocity. This was not a marginal shift. It was not a rounding error. It was a dramatic surge in speed. Furthermore, the nature of this change was disturbing. In natural events, sudden changes are usually chaotic. An explosion, a collision, or a violent fracture. But this was smooth. It was timed. And most critically, it was directed. The object was not accelerating outward toward the galactic void as it left the solar system. It was accelerating inward. It was bending its arc, tightening its curve closer to Earth by several measurable degrees. The evidence for this acceleration was not limited to optical telescopes, as the Earth rotated and brought different instruments to bear. Doppler radar arrays began to interrogate the object by 0505 Universal Coordinated Time. The radar returns confirmed what the cameras were seeing. The radar picked up a distinct spectral shift. This is a change in the frequency of the signal bouncing off the object, which allows scientists to calculate speed with incredible precision. The numbers were staggering. The object was now traveling faster by a factor of 33 compared to its motion just 1 hour prior. To put that in perspective, natural comets do speed up and slow down, but they do so gradually over weeks or months as they interact with gravity and heat. A sudden multiplier of 33 is not just statistically significant, it is effectively impossible under the known physics of natural comets. The standard model for cometary acceleration relies on a phenomenon called outgassing. As a comet gets closer to the Sun, the heat causes the frozen gases on its surface to sublimate, turning directly from solid ice into gas. This gas shoots out into space, acting like a weak, natural thruster. It pushes the comet in the opposite direction. This is the rocket effect. However, the force generated by natural outgassing is tiny. It creates fractional increases in speed, small nudges that accumulate over time. For 3I Atlas to achieve the acceleration recorded on December 16th, the physics required are entirely different. To jump in speed by a factor of 33 in less than an hour would have required an energy release several orders of magnitude beyond normal sublimation. If this were a natural event, it would have been violent. The surface of the comet would have had to explode outward to generate that much thrust. Astronomers looked for the aftermath of such an explosion. They scanned for a cloud of debris. They looked for visible fragmentation, where the main body splits into smaller rocks. They looked for dust ejection or a chaotic spin caused by the uneven blast. They found nothing. There was no dust. There were no fragments. The object was not spinning out of control. It was simply moving faster. It was a clean, quiet, and sustained acceleration. Teams at NASA's Jet Propulsion Laboratory in California immediately shifted into high gear. Their task was to recalculate the future path of the object based on this new reality. The old models were useless. The new arc, calculated with the fresh velocity data, brought 3I Atlas measurably closer to Earth. It is important to clarify that this was not a collision course. The object was not aiming to hit the planet. However, it was no longer following the outbound projection that every astronomer had been working with. The implications were immediate and profound. Every predictive model based solely on gravitational forces, the standard way we map the solar system, had to be scrapped. Gravity pulls objects in predictable curves. It does not cause them to suddenly sprint forward. This was not random turbulence. This was a course correction. As the morning progressed, the data began to break expectations even further. The acceleration event was not invisible. It coincided perfectly with a sudden brightening of the object on its sunward side. A flash of light was recorded, lasting just under 4 minutes. This flash was observed independently by the European Space Agency's Solar Orbiter probe and ground-based observatories in the southern hemisphere. The timing was too precise to be a coincidence. The acceleration, the trajectory bend, and the light flare all occurred within the same narrow observational window. It was a synchronized event. By the time the sun rose over the Pacific Ocean, planetary defense teams had added 3I Atlas to the real-time watch list. This classification is reserved for objects that require constant monitoring. They did this not because the object posed an immediate threat of impact, but because no known natural object had ever behaved this way in the history of recorded astronomy. The world's most advanced instruments were now locked onto one question: what had triggered the spike? The physical condition of the comet offered no clues. Its surface showed no signs of a break or a crater from a collision. Its light curve, the graph of its brightness over time, remained clean after the flare subsided. Its rotational axis held steady, meaning it wasn't wobbling. And yet, it was moving 33 times faster than it had been the day before. Something had changed the rules. For the first time in this encounter, the motion itself became the anomaly. To understand why this is so disruptive to scientific consensus, we have to look at how we understand celestial mechanics. When interstellar objects enter our solar system, their paths are governed by predictable mathematics. From the moment they are detected, observatories begin computing orbital solutions. These are complex equations that determine not just where the object has been, but exactly where it is going. This is Newtonian physics applied at a massive scale, refined by centuries of observation and calculation. Until December 16th, 3I Atlas was a textbook example of these laws. Its trajectory was hyperbolic. In simple terms, this means it was moving too fast to be captured by the sun's gravity. It was not going to settle into an orbit like a planet or a periodic comet. It entered fast. It was scheduled to pass near the inner planets, and then it would be flung back out into the galactic wilderness. Its path would be slightly curved by the sun's mass, but that curve was calculable. The projections were based on millions of data points. There was virtually no uncertainty. The expected closest approach to Earth had been logged, calculated, and filed weeks in advance. The distance was safe 1.88 astronomical units. That is more than 260 million kilometers. A distant flyby that would barely register to the naked eye. But when the velocity spike occurred, all of those predictions broke. Orbital solutions are built on the assumption that acceleration is caused only by gravity. In rare cases involving comets, astronomers add a small variable for non-gravitational acceleration caused by outgassing. As discussed, a little extra heat causes a little more sublimation, which produces a small puff of gas. That gas escapes unevenly and nudges the object slightly off course. These nudges are slow, cumulative, and often noisy, meaning they create wobble and dust. With 3I Atlas, the shift was not slow, it was not noisy, it was immediate, linear, and smooth. When the data teams at the Jet Propulsion Laboratory reran the orbital solution using the updated velocity, they realized that 3I Atlas was no longer following a purely hyperbolic path. The arc had fundamentally changed. Instead of drifting further from Earth with each passing hour as predicted, the object had carved a new lane. This new lane brought it closer. Again, it was not an impact trajectory. but it was an approach that required a complete rewrite of every simulation. The computer models struggled to fit a natural curve to the new data points, and here is where the analysis becomes truly disturbing. The direction of the acceleration was not random. In a natural outgassing event, gas jets can erupt from anywhere on the surface, pushing the comet in random directions sideways, backwards, or tumbling it over. But the vector of acceleration for 3I Atlas was specific. It was aligned almost perfectly along the Sun vector. The Sun vector is the imaginary line connecting our planet to the Sun. The object accelerated in a way that kept it strictly oriented along this line relative to the observation points. In other words, the acceleration wasn't just faster, it appeared to be targeted. It utilized the geometry of the solar system. Gravitational models alone could not explain this alignment. Gas-based thrust models also broke down when faced with the numbers. Scientists tried to simulate a natural scenario where a pocket of ice exploded to create this thrust. But the math did not work. No known comet has ever produced enough mass ejection in such a short time to cause a 33-fold change in velocity without destroying itself. And even if a comet had somehow survived such an explosion, the result would have been chaotic. We would see erratic spin. We would see an uneven tail formation. We would see a visible loss of cohesion as the object crumbled. None of those signatures were present. The object remained solid. It remained stable, instead of a crumbling rock. What emerged from the data processing centers was something uncomfortably close to an engineered curve. The motion profile resembled a probe adjusting its flight path with precision timing, executing a burn to alter its destination. This suspicion was reinforced as the velocity numbers settled into the servers at the European Space Agency. When scientists fed the fresh data into their internal projection software, what they saw on their screens added a new layer of complexity to the event. Zooming in on the acceleration curve, the graph showing how the object gained speed over time, they noticed a distinct profile. In nature, when a comet accelerates due to outgassing, the graph is often jagged. Gas vents open and close randomly. Pressure builds and releases in uneven bursts. It looks like noise, but the graph for 3I Atlas was different. It showed a smooth, calculated rise in speed, followed by a short, steady plateau where the velocity held constant, and then a return to stability. To an aerospace engineer, that pattern is unmistakable. It does not resemble the chaotic behavior of a sublimating rock. It resembles the thrust profile of a guided vehicle. It mimics the burn of an engine throttle up. Hold for course correction. Throttle down. It implies control. Publicly, the scientific community remained cautious. Press releases and official statements emphasized the need for more data, sticking to the safe narrative of a peculiar cometary event. But internally, inside the quiet rooms of mission control centers, the tone had shifted. The mood was no longer one of curiosity, it was one of concern. This was no longer just a comet that defied classification. It was a massive body that had autonomously changed its direction, altered its speed, and fundamentally rewritten its entire outbound trajectory. And perhaps most disturbingly, it had done so without any known external force acting upon it. There was no collision. There was no gravitational assist from a planet. It simply moved. And because of that move, Earth was no longer a bystander watching from the sidelines. We were now effectively on the curve. To understand why this is so bizarre, we must look at the basics of comet physics. In the Standard Model, cometary tails are simple structures. A comet falls toward the sun. Solar radiation heats the nucleus. The ice on the surface turns into gas, carrying dust with it. This material is then pushed away by the relentless stream of particles known as the solar wind. The result is a long, flowing tail that always points away from the sun. It acts like a windsock in a gale. It does not matter which direction the comet is traveling. The tail is a reaction to solar pressure, not a product of the comet's own motion. But 3I Atlas does not follow this script. It never has. And on December 16th, just as its trajectory veered closer to Earth and its velocity spiked 33 times higher than expected, another anomaly flared back into view, the anti-tail. Most observers had written off this feature weeks earlier. Back in early November, several high-resolution images had captured a faint, ghostly structure pointing in the completely wrong direction, not away from the sun, but directly toward it. At the time, the consensus was to dismiss this as a visual illusion. Astronomers call this a projection effect under certain orbital geometries. As Earth passes through the plane of a comet's orbit, the trail of heavy dust particles left behind weeks ago can appear. From our perspective, to point toward the sun, it is a trick of the eye, a result of viewing a three-dimensional dust field from a specific angle. But the event on December 16th was different, just minutes after the acceleration began. The anti-tail of 3I Atlas reappeared, and this time, it was not a faint optical smear or a trick of perspective. It was defined. It was sharp. It was energetic. Images captured by the Very Large Telescope in the high desert of Chile showed a distinct sunward spike emerging directly from the nucleus. This spike coincided perfectly with the timeline of the velocity shift. The structure held steady for nearly 20 minutes. A coherent beam of material or light projecting forward. Then, as the acceleration event concluded, it began to fade, slowly dissolving back into the solar glare. What made this reappearance scientifically compelling was its behavior. The anti-tail didn't just passively exist, it pulsed. 3 distinct brightness peaks were recorded in rapid succession. Each pulse aligned perfectly with a momentary increase in reflected light from the object's sun-facing side. This is not how natural outgassing works. Natural jets are messy. They spray material in wide cones. They cause the comet to spin. They vent from irregular cracks on the surface, flaring in unpredictable directions based on the shape of the nucleus. But what 3I Atlas showed was geometric consistency. The anti-tail pointed almost exactly along the solar vector. It looked as if mass or energy was being ejected not away from the sun, but directly toward it. In terms of physics, ejecting mass forward is how you slow down or change direction against the flow of gravity. It is the equivalent of a spacecraft firing its retro rockets. It is the equivalent of turning on an engine pointed at the very thing you are supposed to be escaping. And yet, the data suggests that is precisely what happened. Spectral readings taken during this event added more layers to the mystery. When astronomers analyze a comet's tail, they look for chemical signatures, fingerprints of the gas being released. They expect to see hydroxyl, carbon monoxide, or ammonia. But the instruments trained on the anti-tail of 3I Atlas picked up none of these. Instead, they detected reflected sunlight. There was no chemical tail. There was no sublimation plume. There was just pure, broadband reflected light, structured into a tight arc pointing back toward the star. Some scientists proposed that a reflective surface on the comet had briefly activated. Perhaps a patch of metallic ore or a smooth crystalline layer of ice had caught the sunlight at just the right angle. Others speculated it was a dust flare, a sudden cloud of highly reflective particles. But these explanations fail to answer the central question: why was this feature perfectly aligned with the acceleration vector? Because if the anti-tail is real, if it is not just a visual illusion, and not just passive dust floating in the orbital plane, then it represents thrust. In the vacuum of space, action and reaction are absolute. If 3I Atlas is ejecting mass or energy in one direction, it must move in the other. And if it is ejecting it toward the sun at the exact moment it accelerates, then what we are seeing is not a comet responding to heat. It might be an object that is using the sun to move, as the world's top observatories work to recalculate the trajectory in the hours following the event. A quieter, less publicized data stream arrived from the European Space Agency's Solar Orbiter. This spacecraft, currently operating near the inner solar system, carries an instrument package tuned to measure the flow of light and scattering in the heliosphere. It had been passively tracking the interstellar object as it crossed one of its observational sectors. What the solar orbiter caught was subtle, but crucial. It did not see a jet. It did not see a thermal signature of heat. It did not see an outburst of dust. It saw a flash. For just under 4 minutes, the light profile of 3I Atlas changed dramatically. The data showed a sharp rise in reflectivity, followed by a symmetrical drop. It was precise. This was not the irregular flicker of loose rocks tumbling in space, which reflects light in chaotic, jagged patterns. This was a clean spike. The light intensity rose quickly to a peak and then faded down the same slope. To the analysts looking at the waveform, it looked engineered. At first, the team interpreted this anomaly as a calibration error, perhaps sunlight reflecting off background dust, or a glint caused by the specific geometry of the phase angle, the angle between the sun, the object, and the sensor. But that explanation failed when they checked the alignment. The flare occurred at an angle that could only be explained if a highly reflective surface, one that is flat, smooth, and directional, had briefly aligned itself between the sun and the Earth. And crucially, this alignment happened at the exact same moment the anti-tail flared and the object accelerated. When this data from the solar orbiter was layered on top of the optical imagery from the Very Large Telescope and the spectral shift from the Mount Lemmon survey, a coherent pattern began to emerge. We were not looking at isolated anomalies. We were looking at a system. Motion, thrust, and reflection were all tied together. The light profile indicated an albedo or surface reflectivity that peaked above 90% during the flare. In nature, very few things are that reflective. Fresh snow or ice can reach high albedos, but they scatter light in all directions. A mirror reflects light in a focused beam. The data from the solar orbiter suggested that 3I Atlas was behaving like a mirror, but comets do not have mirrors. At least, not ones made of natural materials. Ice reflects, but it diffuses the light. Organic compounds on the surface of asteroids absorb light, making them dark. Even highly processed regoliths never return light in such a focused, high-intensity band. And yet, 3I Atlas showed no signs of the physical changes that would create a natural mirror. It hadn't cracked open to reveal a fresh core. It hadn't tumbled to show a new side. It remained physically unchanged. Yet its optical behavior had shifted radically. And so, another possibility began to circulate. It started cautiously, discussed only in secure channels and behind closed doors. What if this reflection wasn't an accident of geology? What if it was a result of orientation? Consider the hypothesis that a surface, whether artificial or simply non-random in its structure, aligned itself specifically to reflect light back toward the sun. In physics, we know that light carries momentum. Photons have no mass, but they have energy. When they strike a reflective surface and bounce off, they transfer a tiny amount of that momentum to the object. It is a push. This force is small. It is incredibly weak compared to a rocket engine, but in the frictionless environment of space, if the surface area is large enough and the alignment is precise enough, that pressure can be used to steer. This is the principle behind solar sailing, a method of propulsion that human engineers have already tested with missions like Icaros and LightSail. So, here is the unsettling question that the data forces us to ask. Did 3I Atlas just perform a maneuver? The sequence of events suggests a coordinated action. A reflective surface aligns. A flare is produced. An anti-tail forms along the solar vector, and the trajectory shifts. That sequence reflection followed by motion implies coordination. It is the kind of sequence we program into our own spacecraft. It is the kind of physics we simulate in our laboratories, but it is the kind of behavior we have never, in the history of astronomy, observed in a visitor from interstellar space, because such a conclusion challenges the foundations of astrophysics. The scientific community spent weeks searching for a more comfortable explanation. When the object first began its sudden acceleration on December 16th, the immediate instinct of every astronomer was to reach for the most traditional tool in the box: outgassing. This is a standard phenomenon in comet science. The mechanism is simple and well understood. As a comet approaches the sun, solar radiation heats its icy surface. The ice sublimates, skipping the liquid phase and turning directly from a solid into a gas. This gas, expanding rapidly, shoots out into the vacuum of space, according to Newton's third law of motion. For every action, there is an equal and opposite reaction. The pressure of that escaping gas pushes against the nucleus of the comet like a jet engine, generating a small amount of thrust. In theory, if you have enough of these microjets firing, they can change a comet's trajectory. It is real. It has been observed in thousands of comets. And for most visitors to our solar system, this explanation works perfectly. But as the data from December 16th was dissected, it became increasingly clear that what happened with 3I Atlas was not outgassing. It did not even look like a distant cousin of outgassing. The problem lies in the nature of the process. Sublimation is inherently messy. It is chaotic. It is rarely uniform. And, crucially, it is almost never timed with precision. When a natural comet warms up, the process is gradual. Gas escapes unevenly from the sun-facing side because the surface is not smooth. It is rugged, filled with craters, cracks, and ridges. Sometimes, a jet will fire from a specific angle, acting like a thruster on the rim of a wheel, causing the nucleus to spin or wobble. Sometimes, the internal pressure builds up behind a crust of ice until it fractures the surface, creating a violent outburst and sending shards of debris flying. All of this makes the motion of natural comets jittery and unstable. Even the most well-behaved comet will show random variances in brightness, spin rate, and trajectory as it vents. 3I Atlas did none of that. The motion recorded on December 16th was clean. It was, in a word, clinical. The velocity increase was rapid, yet smooth. It followed a specific curve, a ramp-up, a hold, and an abrupt end. It was not a noisy dataset filled with random spikes. It looked like a single, deliberate pulse, as if one coherent force had pushed the object into a new path and then simply switched off. That kind of behavior is incompatible with the physics of sublimation. When scientists at major institutions tried to reverse engineer the event, calculating how much gas would be needed to accelerate an object of 3I Atlas's estimated mass by a factor of 33, the results were startling. even under the most generous assumptions. The amount of sublimated gas required to produce that specific change in velocity would be enormous. We are talking about the equivalent of ejecting thousands of tons of material within a matter of minutes. If that had happened, the object would have been practically screaming at our sensors. We would have seen a massive dust cloud blocking the stars behind it. We would have seen a dramatic brightening of the surface as fresh ice was exposed. We would have seen an increase in the density of the coma, the atmosphere around the comet. Yet, there was nothing. Instruments designed to track infrared signatures specifically tuned to detect the heat radiated by escaping dust and gas showed flat lines during the event. Spectral analysis from the James Webb Space Telescope, the most sensitive infrared observatory humanity has ever built, scanned the object for chemical fingerprints. It looked for water vapor. It looked for carbon monoxide. It looked for the telltale signals of a major molecular release. It found none. The only thing the sensors recorded was an increase in reflectivity, a brief optical spike, and then movement. And if the lack of physical evidence wasn't enough to bury the outgassing theory, the geometry of the event served as the final nail in the coffin. In a natural scenario, sublimation occurs on the hemisphere facing the sun, because that is where the heat is. The jets push material away from the sun, creating a recoil force that pushes the comet away from the star. But the motion of 3I Atlas defied this logic. The acceleration vector was aligned with the solar vector. The push did not come from beneath the object to lift it away. It appeared to come from the sunward side, driving it along the line of sight. It was as if the object had activated a mechanism precisely aligned with the sun. This does not fit standard comet models. It does not even fit the exotic models used for rare, volatile-rich comets. In those models, you would expect to see a rotation wobble. If a massive jet fires from one side of a rock, that rock will spin. It is inevitable. But no axis change was detected. No spin-up effect accompanied the surge in speed. Instead, 3I Atlas remained perfectly stable. Its orientation was locked. It moved less like a tumbling rock and more like a stabilized craft. Some astrophysicists attempted to salvage the natural explanation by proposing complex scenarios: hidden vents, internal pressure reservoirs that vented symmetrically, or delayed phase changes in exotic ices that we haven't seen before. But every layer of complexity added to the model only created more unanswerable questions. How could something eject so much mass without leaving a trace? How could it push in the wrong direction relative to the heat source? How could it do so silently? At some point in scientific inquiry, the simplest answer, however unsettling, becomes the most probable. It wasn't outgassing. It was control. To understand the gravity of this conclusion, we have to look at how we predict movement in space. In astronomy, when an object moves through the solar system, its path is governed by one primary, overwhelming force: gravity. It is the same law whether you are tracking a grain of sand, a planet, or an interstellar visitor. The equations are old, precise, and deeply trusted. When a new comet is identified, astronomers use these gravitational models to forecast its path months or even years in advance. They factor in the sun's massive pull, the subtle tugs of Jupiter and Saturn, and the object's orbital inclination. The results are typically reliable to within a fraction of a percent. So reliable, in fact, that our entire planetary defense system depends on them. But on the morning of December 16th, those models stopped working. When 3I Atlas accelerated, it did not do so in a way that gravity could explain. There was no nearby planetary mass to pull it off course. It did not pass close to Mars or Earth. There was no asteroid collision to nudge it. There was no tidal interaction strong enough to account for the shift. And yet, the velocity changed. When the motion was logged and plotted, astronomers were forced to label it with a term they reserve for the unexplained non-gravitational acceleration. In the sterile language of academic papers, this phrase is often used to describe the small, cumulative adjustments caused by outgassing over months. But in the case of 3I Atlas, the term took on a different weight. This wasn't small, and it wasn't cumulative. It was instantaneous. The curve of acceleration looked designed. It started with a slow increase, measurable. Yes, but subtle enough that it could be mistaken for observational drift or sensor noise. Then, it rose sharply, peaking with a clean upward slope before settling into a new, steady velocity. There were no oscillations. There was no hunting for the correct path. It was one smooth push, like a glider catching a controlled gust of wind and then coasting on the new heading. Data from NASA's Jet Propulsion Laboratory confirmed what ground-based telescopes had already hinted at. The trajectory had shifted by a measurable degree. And more than that, the direction of the force was equally disturbing. It aligned almost perfectly with the solar vector, the imaginary line running from the sun to the object. In basic physics, this is the direction where no propulsion is supposed to occur, because sublimation pushes against the sun. But here, the force moved along the light path. It was responding to the sun directly. Scientists at the European Space Agency and the Max Planck Institute independently confirmed the anomaly. Their internal reports described it with clinical precision, measured delta V, inconsistent with gravitational projection. Motion vector aligned with heliocentric photon path. In plainer terms, the comet moved in a way that shouldn't be possible unless some force was deliberately pushing it. And that push came from the direction of the sun. What is even more compelling is the stability of the motion. No drift, no torque. If this were caused by natural venting, the nucleus would have experienced rotation instability. But 3I Atlas remained stable. It moved like a vehicle under guidance. And so, scientists turned to the math of propulsion. When they calculated the amount of force required to produce the observed trajectory shift, one surprising conclusion emerged. The values matched what would happen if the surface of 3I Atlas had reflectivity levels near that of polished metal. And if the object was catching and converting photon pressure from the sun into momentum, this brings us into the domain of solar sails. This is a method of propulsion that uses light itself. Photons strike a reflective surface and bounce off. In that bounce, they transfer momentum. It is a concept we have theorized, tested, and even deployed in small forms on Earth-based missions. But we have never seen it used by something that arrived unannounced from interstellar space. Non-gravitational forces can be explained by gas, by geometry, or by thermal pressure, but only to a point. 3I Atlas had passed that point. It did so quietly, precisely, and deliberately. This brings us back to the visual evidence. In every textbook on comet behavior, one principle remains constant: tails point away from the sun. It does not matter where the comet came from. It does not matter which direction it is moving. The solar wind and radiation pressure push dust and gas outward, forming a tail that stretches behind the object in the anti-solar direction. This rule is so foundational that even anomalies usually adhere to it in general terms. But 3I Atlas seems determined to rewrite every rule we thought we understood, because what happened on December 16th wasn't just an acceleration. It was an event accompanied by the resurgence of something far more difficult to explain: a tail pointing toward the sun. This wasn't the first time astronomers had observed a sunward structure. Earlier in November, several observatories, including the Very Large Telescope and the Subaru Telescope, recorded a narrow feature extending opposite the main dust tail. It was aligned almost directly back toward the solar disk. At the time, the scientific community was comfortable dismissing it. The feature was faint. It was interpreted as an observational artifact, a so-called anti-tail illusion. These illusions are a known phenomenon. They occur when Earth travels through the plane of a comet's orbit. From our vantage point, the geometry causes older, slower dust particles trailing behind the comet to visually overlap, appearing to point toward the Sun due to foreshortening. It is a trick of perspective, a 2D flattening of a 3D structure. That is how we explained it in November. But that explanation collapsed on December 16th, because the anti-tail came back. And this time, the geometry was different. Earth was no longer in the orbital plane that creates the illusion. The angles didn't support the trick of light theory. This was a physical structure, appearing exactly when the object accelerated, pointing exactly where the thrust vector indicated it should. But mere appearance was just the beginning. On that morning, after the velocity spike had already been confirmed by radar and optical sensors, the behavior of the object shifted again. The anti-tail did not just reappear in the data streams. Effectively, it ignited. For a duration of nearly 20 minutes, observatories recorded a structured, high-intensity stream of material. This was not a vague cloud. It formed a tight, sunward extension projecting from the nucleus. In the lexicon of cometary science, tails are usually described as diffuse or scattering. They spread out like smoke in a breeze. But this feature was sharp. It was linear. It was collimated, meaning the sides of the stream were parallel, like the beam of a spotlight rather than the glow of a lantern. And critically, its appearance was timed precisely with the start and end of the object's acceleration event. This visual clarity killed the optical illusion theory instantly. Illusions caused by orbital perspective do not have sharp edges, and they certainly do not turn on and off like a switch. Furthermore, unlike a trick of the light, this structure cast a detectable physical signature. Spectrographic data from telescopes in both Hawaii and Chile revealed the internal dynamics of the tail. By analyzing the light shifting toward the red or blue end of the spectrum, astronomers could measure the velocity of the particles within that stream. The results were conclusive. It was not static dust hanging in space. It was not sunlight refracted through a cloud of gas. It was matter, physical mass moving at high speed, and it was moving directionally, flowing strictly along the solar vector, directly toward the Sun. That is when a new and unsettling theory began to circulate among dynamic modelers and orbital physicists. They had to ask the question, what if this wasn't a tail at all? What if we were looking at exhaust? In classical Newtonian physics, the rules of motion are absolute. Every action has an equal and opposite reaction. This is the bedrock of rocket science. If an object expels mass in one direction, the main body must move in the opposite direction. It does not matter if you are throwing rocks, venting gas, or firing ions. The math is the same. Rockets operate on this principle. Gas jets on satellites operate on this principle. If 3I Atlas was expelling material toward the Sun, not away from it, as natural solar pressure would dictate, then the acceleration toward Earth becomes mathematically explainable. It ceases to be chaos. It becomes propulsion. The anti-tail flared in perfect alignment with the vector of movement required to flatten the orbit. The timing reinforced this conclusion. The stream appeared exactly when the acceleration began, and it vanished the moment the motion ceased. This one-to-one correspondence is not something you see in natural outgassing. Natural jetting from comet surfaces is a messy, sluggish process. It is sporadic. It is influenced by the rotation of the comet, by the uneven heating of the surface, and by the chemical composition of the ice. It lags behind the heat source and lingers after the peak heat is gone. But this event looked like a maneuver. Some scientists at the European Space Agency began referring to it informally in their internal memos as the sunward impulse. The concept was simple physics: eject material toward the star to gain momentum in the opposite direction. And when they ran the numbers, the math worked. Even small amounts of ejected dust or gas, if released at a high enough velocity, could generate the kind of non-gravitational acceleration that was observed. But while the math worked, the natural history did not. No natural comet has ever done this deliberately. Comets do not eject mass with precise timing. They do not generate thrust from a preferred hemisphere to stabilize their flight. They do not exhibit coordinated geometry between tail formation and a targeted motion vector. Unless, of course, this wasn't a natural tail at all. Unless the anti-tail is not a flaw in our perspective, but a feature of a system designed to push itself forward by pointing straight at the sun and firing. This brings us to the most troubling aspect of the December 16th event: the energy. At the heart of every physics equation lies one unbreakable law: the conservation of energy. Energy cannot be created from nothing. It can be transferred. It can be converted from one form to another. It can be stored, but it cannot be spontaneously generated. This rule is what allows scientists to trust the numbers. If you can measure the energy going into a system, you can predict the energy that comes out. Comets, despite their reputation for unpredictability, follow this logic strictly. When a comet approaches the sun, it acts like a passive engine. It absorbs solar radiation. That heat energy causes phase changes in the ice, turning it into gas. The kinetic energy of the escaping gas pushes the comet. It is a closed loop. The sun provides the fuel. The comet converts it into motion. It is a slow, inefficient process driven entirely by the intensity of the sunlight. But on December 16th, 3I Atlas violated the balance sheet. When the object's velocity spiked by a factor of 33, scientists across the world's observatories scrambled to quantify the forces involved. The first step was a standard calculation. They determined the total kinetic energy required to accelerate a mass of that size, estimated at 5 kilometers in diameter, to the new velocity recorded by radar. The result was staggering. The energy shift was in the realm of high-scale propulsion systems, far beyond what any natural comet should produce in such a short window of time. Then came the harder question: where did that energy come from? We know exactly how much energy exists at that location in space. At 1.8 astronomical units from the sun. The solar flux, the amount of sunlight hitting a specific area, is a known constant. We can calculate it down to the watt. An object the size of 3I Atlas would be receiving a specific limited quantity of energy per second, even if its surface was perfectly black and absorbed every single photon. And even if it converted that heat into thrust with 100% efficiency, which is physically impossible, the amount of usable energy would still be limited. That number didn't match the output. It wasn't even close. To accelerate an object of that mass by the amount recorded, the solar input would have to be not just absorbed, but multiplied. The energy output observed in the movement was significantly higher than the solar energy available to creating it. It was like watching a car accelerate from 0 to 60 miles per hour on a teaspoon of gasoline. It defies the efficiency curves of natural physics. The math began to collapse. Engineers at NASA's Goddard Space Flight Center ran internal simulations trying to force the model to work. They used best-case assumptions. They modeled the surface with high reflectivity. They optimized the angles to the solar vector. They even input exotic material response curves, assuming the comet was made of volatile substances that explode easily. Still, they fell short. The input did not match the output. To account for this shortfall, the scientific community had to look for hidden energy. Some proposed the idea of stored thermal energy. The theory was that perhaps the object had absorbed heat when it was closer to the sun, though it hadn't been closer yet, or perhaps it retained primordial heat deep within its core. And for some reason, it released it all in one controlled burst. But that idea raised more problems than it solved. Comets are terrible at storing heat. They are made of ice and porous rock, which are insulators. Heat takes a long time to penetrate, and it takes even longer to release. It does not vent in a sudden 20-minute spike unless the object breaks apart. And as we know, 3I Atlas did not break. Others proposed exotic sublimation. They suggested that maybe the surface wasn't composed of traditional water or carbon dioxide ice, but of volatile, unstable compounds we haven't encountered in our solar system. Some suggested amorphous ices or cryogenic materials that can undergo rapid phase transitions, effectively exploding when triggered by a specific temperature. But even these exotic models failed to explain the data. If a massive chemical explosion or phase change had occurred, it would have generated heat. A lot of heat, but the infrared telescopes watching the event saw nothing. This thermal silence is perhaps the most damning piece of evidence. There was no heat spike. There was no visible gas plume expanding in all directions. There was no rotating venting behavior. There was just light and motion. This leads to a concept physicists call an energy budget violation. If the energy didn't come from the sun directly, and it didn't come from internal heat, and it didn't come from a chemical reaction, then what remains? What kind of system can output more kinetic energy than it appears to absorb from its environment? It forces a reassessment not just of the event, but of the object itself. Because if 3I Atlas is moving without paying the energy cost that nature demands, then maybe it is not using energy the way we expect a rock to use energy. With 3I Atlas accelerating at a rate that shocked every observatory on Earth, the focus shifted to an uncomfortable question. If this energy didn't come from sunlight, could it have come from within? The idea of stored internal energy inside a comet isn't entirely new. We know that radioactive decay can warm the cores of large asteroids over millions of years. But the way this object acted made even seasoned planetary scientists rethink what a comet actually is. Let's look at the standard model one more time. When comets journey toward the inner solar system, they are passive travelers. They wait for the sun to wake them up. They absorb heat. That heat causes sublimation. The gas escapes. It is a reactive process. Occasionally, heat penetrates deeper into the nucleus, finding pockets of pressure in fractures or cavities. This can cause jets, but even then, the process is chaotic, inefficient, and slow. 3I Atlas, however, behaved like a system that had planned its release. The sudden 33-fold acceleration, absent any visible outgassing or structural fragmentation, strongly suggested that the energy had been contained. It implies a reservoir of power that was tapped, regulated, and then shut off. This raised the unsettling prospect of an internal power source. But the problem with this theory, for a natural object, is scale. To store that amount of potential energy in a natural lattice of ice and rock is chemically difficult. To release it directionally is geometrically improbable. And to do so without melting the entire surface of the object is thermally impossible. Unless the object is not made of ice and rock, this conclusion is driven by the sheer thermodynamics of the maneuver. To generate the kind of kinetic burst observed on December 16th, 3I Atlas would have needed to tap into a reserve of energy that defies natural explanation. Specifically, if we assume this was a thermal event, the object would have had to retain more heat energy than any comet in the history of astronomy. And not just a marginally larger amount, we are talking about orders of magnitude more. If that heat had been accumulated during previous encounters with other stars, or even during its approach to our own sun, it should have left a trail. Heat, in the vacuum of space, is hard to hide. Infrared observatories like SOFIA, the Stratospheric Observatory for Infrared Astronomy, would have picked it up. The thermal imaging sensors on the James Webb Space Telescope would have detected a distinct warming curve, or at least a set of localized hotspots on the surface where the heat was leaking out. But none of that data existed. In fact, the object's infrared signature in the hours leading up to the event was completely flat. There was no thermal buildup. There was no glowing core. There was just the cold, inert body of a typical comet, or so it seemed. This thermal silence forced scientists to consider a second, more radical possibility. Maybe 3I Atlas wasn't storing heat. Maybe it was storing energy in a completely different way, not thermally, but structurally. Materials science tells us this is possible. There are substances, both synthetic and theoretical, that can undergo rapid internal phase changes. Think of them like molecular springs under extreme tension. They hold potential energy within their very atomic lattice. Given the right stimulus, a specific temperature, a frequency, or a signal, they snap into a new configuration. When they do, they release vast amounts of stored energy instantly. Could the body of 3I Atlas be composed of such material on Earth? We have engineered shape memory alloys, metals like nitinol that return to a preset form when heated. We have developed metastable ceramics that exhibit rapid energy release when exposed to specific radiation bands. But to embed such behavior into an object the size of a mountain, and then to trigger it at precisely the right orbital moment, would imply more than just unique geology. It would imply an architecture. It would imply something designed. This is where the discussion within the scientific community began to fracture. One camp held fast to naturalistic explanations. They argued that perhaps we were underestimating the object's mass, or overestimating its speed. Perhaps the energy came from a compound we simply haven't encountered yet, an exotic form of ice that combusts or decomposes violently when exposed to specific wavelengths of interstellar radiation. But the timing made this defense difficult to maintain. The object didn't randomly vent. It accelerated in direct alignment with its Earth trajectory. Nature is rarely that helpful. Others raise the idea of a pressurized reservoir, a chamber of high-pressure gases trapped deep inside the core, sealed off by a thick crust until now. If such a reservoir suddenly ruptured, it could produce a massive jet. But again, the evidence was missing. A rupture creates debris. It creates a flash. It creates a cloud. 3I Atlas produced only motion. So, we are left with a physics mystery. If the energy didn't come from outside the sun, and it didn't behave like heat stored inside, then what kind of storage system could power that burst? And more importantly, who or what would build it? Normally, when a comet accelerates due to non-gravitational forces, astronomers know exactly what to look for. They turn their instruments toward the object and scan for the signs of an eruption, a jet, a flare, a visible transformation of the tail. These jets are often spectacular events. High-speed columns of gas and dust shoot out from a vent, usually triggered by solar heat reaching a volatile patch of ice buried inside. The comet spins from the torque. The jet pushes like a rocket, and the object adjusts its trajectory. It is inefficient. It is messy. But it is predictable. That is what made 3I Atlas so disorienting. The jet never appeared. On the morning of December 16th, dozens of ground-based observatories and space-based telescopes were watching the event unfold in real time. In the critical minutes following the object's sudden 33-fold acceleration, they waited for the telltale signs. They expected a glowing plume. They expected a burst of particles. They expected a change in the brightness curve as dust scattered the sunlight. Nothing happened. There was no outgassing. There was no distortion of the tail. There was no thermal bloom, the sudden expansion of heat that accompanies an explosion. The comet didn't even flicker. It just executed pure, silent motion. This absence wasn't subtle, it was glaring. Observatories in Hawaii, Chile, and Spain all reported identical datasets. No new tail, no visible jet structure, and absolutely no directional plume to account for the massive force required to move a 5-kilometer object. Even amateur astronomers, watching with modified backyard scopes and CCD cameras, noticed it. The object sped up, but it left nothing behind. So what does that mean? Some scientists propose that the jet might have been invisible, not in the visible light range, but perhaps in the high-frequency or low-wavelength spectrum that optical telescopes can't see. That triggered a frantic wave of spectroscopic scans. Observatories combed through the ultraviolet, X-ray, and even microwave bands, looking for any trace of energetic particles. The result, blank data. If a jet had existed, it left no electromagnetic fingerprint whatsoever. That pushed the conversation toward darker implications. What if there had been no jet because 3I Atlas didn't need one? This led to a new, highly theoretical model: internal mass redistribution. The concept is complex but grounded in physics. Picture an ice skater spinning on a rink. When they pull their arms inward, they spin faster. They haven't added energy. They have changed their moment of inertia. Now, apply that to linear motion in a vacuum. If 3I Atlas possessed internal mechanical components, massive, shifting weights or layered density zones, a rapid DOD, a precise shift of those internal masses could change its inertia. Under the right, highly specific conditions involving interaction with solar gravity fields. This could theoretically alter its trajectory without ejecting a single gram of material. But that theory raised another issue: control. For a natural object to randomly adjust its internal mass distribution in such a precise, stable way, at that exact moment, is statistically impossible. It implies awareness. It implies a guidance system. Then came the telemetry anomaly. In the hours after the burst, a handful of researchers analyzing radar data from the Goldstone Deep Space Network noticed something strange about the object's physical cross-section. The shape had subtly changed. It hadn't shattered. It hadn't deformed in a chaotic way. It had tightened. The radar return suggested that the silhouette had shrunk by a narrow but detectable margin. It was almost as if a layer of outer material had compressed inward. That is not normal behavior for a comet. Comets expand when they heat up, they don't contract. This behavior is more reminiscent of mechanical contraction, a hull tightening, or panels retracting. This led to the field propulsion theory, the boldest idea yet. Maybe the object doesn't emit jets because it doesn't utilize propulsion in the way we understand it. Maybe it operates on a principle we haven't yet grasped, where motion isn't generated through brute force reaction, but through internal field manipulation. inertia, redirection, or even gravitational cancellation. To the public, these ideas sound like science fiction. To the scientific community, they are deeply uncomfortable because they break every rule we've used to interpret space motion for the last century. But the silence, the lack of debris, the absence of a jet, they demand an answer. The question now becomes, what kind of object moves without leaving a trace? And why is it headed toward Earth? In the aftermath of 3I Atlas's sudden acceleration, astronomers found themselves wrestling with a growing list of anomalies. But one theory began to stand out not because it was comfortable, but because it explained what the others couldn't. It is known as the directional pulse theory. At its core, this theory suggests that 3I Atlas did not accelerate because of a traditional outgassing event or a sudden vent of energy. Instead, the object may have emitted a single directional energy pulse, something short, dense, and extraordinarily efficient. But unlike a chemical rocket or a physical explosion, this would be a non-visible, highly concentrated energy release aimed precisely opposite the direction of its new trajectory. No particles, no flash, just pure impulse. The seeds of this theory were planted by a pattern, a timing echo picked up by radio telescopes just minutes before the object's sudden acceleration. The signal wasn't strong. In fact, most observatories missed it entirely, burying it in the background noise of the universe. But two highly sensitive arrays, one located high in the Atacama Desert and one aboard a private European CubeSat, recorded a single broadband distortion in a region of the spectrum that is usually silent. It was wide spectrum, almost like a chirp, a signal that sweeps across frequencies. But it was incredibly short-lived, lasting less than a second. What caught the attention of physicists was not just the sound, but the source. The signal originated precisely behind the object's motion vector. It came from the exact spot where an exhaust plume should have been. If that signal was the exhaust, then it wasn't a jet of gas. It was something closer to a pulse drive. This kind of mechanism has no analog in current human technology. But the physics is sound. A mass traveling at cometary speeds, when pulsed from the rear with sufficient force, could achieve a trajectory shift without a material ejectocloud. This is especially true if the energy release was not material-based, but instead derived from internal pressure fields or artificial magnetic flux compression. It sounds radical, but the only alternative is that the object chose to move in a specific direction and nature didn't play a role. Some engineers compared it to experimental inertial drive systems theorized for interstellar probes. These designs, long dismissed as unworkable with our current tech, rely on compact magnetic fields to generate momentary directional bursts, essentially creating controlled motion from field interference. Until now, such ideas lived only in white papers. But what if they've been achieved, just not by us? As researchers modeled the trajectory change, they realized something even stranger. The acceleration wasn't just a straight line, it matched orbital avoidance behavior. When they overlaid the new path of 3I Atlas against the map of the solar system's magnetic fields, they noticed that the object had veered slightly away from a solar magnetic threshold. This is a region known for unstable flux density, a place where solar storms can be particularly turbulent. In other words, the object may have corrected itself to avoid an invisible hazard. That suggests an awareness of its environment, or worse, navigation. The idea of 3I Atlas having the ability to course correct based on spatial conditions is where the directional pulse theory becomes truly uncomfortable, because now we are no longer talking about accidental movement or random interaction with the sun. We are entertaining the possibility of deliberate maneuvering. This theory gained traction as more data came in. There was no evidence of heat distortion. There was no debris cloud. There was no visible fragmentation, just a sudden burst in velocity, perfectly timed with an audio frequency pulse. And then, silence. That silence is what haunts the radio astronomers most, because whatever emitted that pulse hasn't said anything since. It came, it moved, and it vanished into quiet. No human spacecraft has ever demonstrated that level of controlled propulsion without an enormous support structure, fuel expenditure, or visible reaction. But 3I Atlas, moving faster than ever before, did it in a moment. And the implications of this silence are now being taken more seriously than anyone thought possible just a week ago. The object did not need to push off any physical medium. It did not need to explode chemically. It simply shifted. And if it can do that once, the question that keeps planetary defense teams awake is simple. What else can it do? As 3I Atlas surged forward with this unnatural force, the ripple effects began to appear where few were looking. They did not appear visually in the sky, but digitally, in the scrolling readings of magnetometers scattered across the planet. To understand what happened next, we have to look at the invisible shield that protects our world. Earth is wrapped in a magnetosphere, a vast bubble of magnetic energy generated by the molten iron spinning in our planet's core. This shield is our first line of defense. It responds constantly to the sun. When the solar wind hits us, the shield compresses. When a coronal mass ejection strikes, the shield vibrates, creating geomagnetic storms and auroras. Scientists know what these natural interactions look like. They are messy, they are broad, and they are loud in the radio spectrum. But what happened during the hours after 3I Atlas accelerated was neither routine nor solar in origin. The first anomaly came from a high-altitude research balloon floating above the Arctic Circle, part of a climate monitoring program. Its onboard magnetometer registered a soft, rolling distortion. It wasn't a sharp strike like a solar flare. It was a ripple in the local magnetic field that moved too quickly to be explained by normal space weather models. Just 30 minutes later, a similar pattern was observed in a ground-based sensor grid in northern Canada. Then, the signal appeared in Norway. Finally, it registered at a research station in Antarctica. When scientists laid these detections over a map, a disturbing picture emerged. The waves were not crashing through the system randomly. They seemed to be tracing the outer edges of the magnetosphere, moving in a sweeping arc. It looked less like a storm hitting a wall and more like a beam probing a surface. It was scanning the system. These disturbances were small enough, measured in nanoteslas, to escape public notice. Your compass wouldn't have spun wildly, your GPS wouldn't have failed. But researchers working in the niche field of geomagnetism recognized the pattern. They had seen something similar only once before in recent memory, when a solar synchronous satellite had unexpectedly tumbled out of alignment after interacting with a localized spike in field pressure. That event had left scientists puzzled for weeks. Now, with 3I Atlas in motion, the puzzle was reassembling itself. The connection wasn't just in the shape of the wave, it was in the timing. Analysts discovered that every time the magnetic distortion wave passed a given location on Earth, it coincided perfectly with the point on the globe that was directly beneath the object's projected path. Note the distinction: it was not reacting to where the object was at that moment. It was reacting to where the object was aimed. The implication was simple and staggering. Earth's magnetosphere was reacting in anticipation. It was behaving almost like the water in front of a moving ship, rising up before the hull even touches it. But in this case, The ship was millions of kilometers away. Some at NASA and the European Space Agency quietly began referring to it as pre-contact compression, though no official documentation used the term publicly to avoid alarm. In theoretical physics, this describes a phenomenon where a planetary field subtly realigns itself under the influence of an approaching, highly magnetized body. In theory, this could happen if the approaching object had its own magnetic field, one strong enough to deform the local region of spacetime or to displace the surrounding magnetized plasma of the solar system. This would create a bow shock that travels ahead of the object at nearly the speed of light. This explanation would be easy to dismiss as a coincidence, except for one specific clue found in the data structure. The shape of the field shift on Earth mirrored the asymmetric structure of the antitail observed on the object. What that meant was not fully understood, but the correlation was mathematically precise. Whatever energy or magnetism 3I Atlas was carrying or emitting through that sunward tail, it was interacting with Earth's defensive shell before the object even arrived. It was as if Earth's shield recognized the presence of a foreign body and began adjusting its shape to accommodate the incoming pressure. This is not how things normally work in the solar system. Even massive solar storms require time to arrive. Their interactions are chaotic, splashing against the magnetic field like waves on a rock. But this was targeted. It was timed. It suggested that something embedded within the comet was either communicating with or passively affecting Earth's magnetic envelope with high efficiency. Space weather scientists, initially skeptical of any connection between a distant rock and a local magnetic ripple, were forced to reevaluate their data. One researcher at the Finnish Geomagnetic Institute published an unrefereed paper that began circulating in academic channels. The paper suggested a bold hypothesis that the object's antitail might not be a passive structure of dust at all. Instead, it proposed that the tail was acting as a directional array, a structure capable of inducing microcurrents in planetary fields from a distance. If true, this redefines our understanding of what the antitail actually is. It moves the conversation away from dust stream and toward field projector. We are looking at the possibility of a shaped energy projection system capable of reaching across millions of miles and influencing planetary-scale magnetic environments. There is no confirmed explanation yet, but the magnetic silence that followed the wave is what troubled the experts most. Usually, after a magnetic disturbance, there is ringing a period of noise as the field settles back down. But here, there was nothing. It wasn't a storm. It wasn't noise. It was a whisper, and Earth was listening. But the anomalies were not confined to our planet. Far beyond the orbit of Neptune, past the cold, dark stretch of the Kuiper Belt, lies the heliopause. This is the boundary where the solar wind, the stream of particles from our sun, finally slows down and yields to the vast, crushing pressure of the interstellar medium. It is the bubble in which our solar system lives. For decades, it has been a quiet edge, barely touched by our instruments. But on the morning of December 16th, something reached back from that boundary. And it wasn't the solar wind. The initial anomaly was picked up by Voyager 1, the aging probe. Launched in the 1970s, is still limping along on its one-way trajectory into the outer darkness. Its instruments are old. Its power is fading. But it is still listening. The probe sent back a series of rhythmic fluctuations in particle density that were immediately flagged by the Deep Space Network as a long-range echo. It wasn't the presence of the particles themselves that caught scientists off guard. Space is full of particles. It was the pattern. There was a resonance in the data, a faint but consistent rise and fall in the signal strength. It mimicked a previous anomaly recorded weeks earlier when 3I Atlas had passed near the heliospheric current sheet between Saturn and Uranus. But this echo was reversed. The telemetry suggested that the signal wasn't being emitted outward into the galaxy. It was being reflected back in. What could create such an echo from the heliopause? In space, there is no hard surface. There is no wall. There is no mirror to bounce a signal off of. The heliopause is a transition zone, a dense mesh of magnetic turbulence where interstellar fields crash into the outer influence of the sun. The answer, buried in layers of theoretical physics, lies in the structure of interstellar pressure. When a dense, structured object creates a disturbance, especially one moving with directional force, like 3I Atlas, it sends ripples outward through the plasma of the solar system. Think of it like a sonar ping in a submarine. Researchers began modeling the delay between the acceleration of 3I Atlas and the return of the echo detected by Voyager 1. The timing was almost too perfect. It matched the speed of a magneto-hydrodynamic wave traveling to the edge of the system and bouncing back. This suggested that the comet had not only broken through a local field boundary near Earth, it had triggered a reactive structure at the edge of the solar system. It was almost like sonar, except the sound didn't bounce off a physical object. It bounced off a change in the fabric of interstellar space itself. To the untrained eye, this sounds abstract, but to those who study heliophysics and interstellar dynamics, the implications were sobering. If an object can produce an echo at the heliopause from this distance, it means two things. First, the object is interacting with magnetic fields at a scale of power we didn't expect. Comets do not do that. No dirty snowball has ever created an electromagnetic imprint that travels to the edge of the solar system and returns with a measurable resonance. But 3I Atlas did. And second, the signal didn't decay. In standard physics, interstellar echoes weaken over distance. They lose their form and dissolve into static. But this echo, whatever caused it, held its shape. In fact, the data from Voyager 1 indicated it came back slightly sharpened. It was as though the field boundary itself had focused the response like a lens. The turbulence at the edge of the solar system had taken the scattered signal from the acceleration event and collimated it back toward the source. What was even more unnerving was the direction of the returning pattern. It didn't follow the twisted path of the sun's magnetic field, known as the Parker spiral. It didn't follow the flow of the solar wind. It came back aligned with Earth. This opened a quiet, speculative conversation among astrophysicists. What if the heliopause is more than just a passive field boundary? What if, under the right conditions, it acts like a membrane, one that responds when specific triggers occur? And what if 3I Atlas, in accelerating through the inner solar system, had just hit that membrane at the exact right angle and caused it to pulse back? At this stage, no one in the official scientific community is claiming artificiality. The peer-reviewed papers stick to terms like anomalous plasma interaction and unexpected field resonance. But the geometry of the event is difficult to ignore. An object accelerates toward Earth. A magnetic wave scans our planet, and a signal bounces off the edge of the solar system, returning directly to us. But what scientists are whispering behind closed doors is that this object may be doing far more than simply moving fast. The data suggests it may be activating systems as it moves. The heliopause, the outer boundary of our solar system, was thought to be a silent, passive wall. Now, it echoes like a struck bell, and Earth just heard the ring. As telescopes across the globe locked onto 3I Atlas during its rapid acceleration phase, a new anomaly emerged. This one did not come from the bright core of the object itself, but from the absence it created behind it, a region of optical distortion, faint but measurable, began forming in its wake. Scientists quickly dubbed it the shadow envelope. This was not a typical comet tail made of dust reflecting sunlight, nor was it an anti-tail structure catching light and throwing it back toward the star. This was fundamentally different. The region trailing directly behind 3I Atlas began to show signs of light suppression. It looked as though space itself was bending ever so slightly, dimming the starlight that should have pierced through. It first appeared in layered spectrograms captured by a satellite array in Chile. Hours later, it was confirmed by the European Space Agency's remote optical relay station positioned above the South Atlantic anomaly. When calibrated correctly, both systems detected a strange narrowing in the visible spectrum trailing directly behind the comet. But this narrowing wasn't constant. It appeared only at very specific intervals, timed perfectly with the fluctuations in the object's anti-tail discharge. This wasn't a visual trick caused by atmospheric distortion, and it wasn't data corruption in the servers. Something physical was happening out there. Researchers at Caltech ran simulations overnight and proposed a hypothesis that sent ripples of unease through the astrophysics community. The object, they suggested, might be dragging a field envelope behind it, a wake not composed of mass or dust, but of polarized space. Imagine a bow wave, not of water, but of bent light, a distortion caused not by particulate matter blocking the view, but by rapid movement through charged plasma regions creating a lens effect. If 3I Atlas had passed through an area of high solar magnetic tension and did so at 33 times its earlier speed, it could theoretically warp the local field into a structured afterimage. But the real surprise came when Earth-based sensors noticed the thermal properties of this wake. The darkened envelope was cooler than the surrounding space. This defied intuition. Space is already near absolute zero. But the cosmic microwave background radiation typically provides a consistent, detectable thermal field in every direction. It is the steady hum of the universe. But where the shadow envelope passed, there was a measurable drop in this background radiation. It wasn't enough to freeze sensors, but it was a statistically significant dip. What kind of object leaves behind a region of less heat in its trail? Engines create heat. Friction creates heat. Absence of heat implies active suppression. One idea was posited quietly, not through press releases, but in internal agency bulletins classified as sensitive but unclassified. The envelope could be a byproduct of field shielding, a kind of passive cloaking mechanism. The theory suggests that whatever force drives 3I Atlas is not only emitting forward propulsion, but is also dampening the energy signatures that trail behind it. Not intentionally, perhaps, but as a side effect of its propulsion method. But if this is true, it opens a different door altogether. Because passive cloaking isn't natural. We do not see it in comets. We do not see it in asteroids. We do not see it in any known non-artificial body. And yet here it was, trailing perfectly behind the object, dimming stars, flattening the microwave echo, and cooling the vacuum of space just enough to raise suspicion. No mass, no dust, just a traveling zone of absence. The Hubble Space Telescope was brought online for brief, focused observations at the request of multiple international science teams. Its high-resolution optical cameras captured the envelope in 3-second exposures. The result was the same every time, a soft, lens-like blur, faintly curved, behaving like it was bound to the core of 3I Atlas by an invisible tether. If this envelope is indeed a wake signature, then we are looking at an object not merely passing through space, but interacting with the medium of space in a fundamentally advanced way. And still, there was silence from the agencies. No press statements, no public warnings, Just a few new telescope schedules quietly updated on university servers. And then, the term shadow envelope began appearing in back-channel documents. Something had changed. 3I Atlas wasn't just moving. It was bending the light behind it, and no one could explain why. As observers tracked the object with growing unease, they began focusing not just on its brightness or trajectory, but on the subtleties of its motion, particularly the signals embedded in its light. Doppler shifts are one of the most fundamental tools in astrophysics. They are the speedometer of the universe. They allow us to detect speed, direction, and changes in velocity by examining how light stretches redshift or compresses blueshift as an object moves toward or away from Earth. But on the morning of December 16th, the Doppler signal from 3I Atlas began to behave in a way that defied precedent. It collapsed, not figuratively, not in a dramatic burst of static, but in a slow, measured, and undeniable way, as the object accelerated to 33 times its prior motion. Earth-based observatories expected a sharp blue shift, a telltale compression of wavelengths indicating rapid approach. But instead of intensifying, the signal began to flatten. The expected gradient of velocity disappeared. What was once a clean Doppler arc on the monitors began to stretch, then blur, then level out into near neutrality. This left researchers stunned. If an object is moving faster toward you, the Doppler shift must increase. That is physics. That is how we find exoplanets. That is how we track stars. That is how we measure the speed of a pitcher's throw on a baseball field. Yet, here was an object defying that expectation. Its spectral data was collapsing into a silent plateau. Some initially blamed instrumentation errors. They checked for calibration bugs. They restarted the software processing the light curves. But cross-verification from 3 major spectroscopic arrays in Hawaii, Chile, and Italy ruled out human error. Each system confirmed the same phenomenon. The Doppler signal wasn't responding the way it should. And worse, it wasn't even consistent. It pulsed. This pulsing not random, but rhythmic, suggested some kind of active modulation. It looked as if the object was controlling the emission profile of its own light. Or perhaps more eerily, it was shielding the true nature of its motion behind some mechanism embedded in its trailing envelope. The pulse frequency appeared to correlate faintly with the anti-tail fluctuations observed just days before. And then, scientists at the Naval Research Laboratory noticed something else. The Doppler flattening was most severe when 3I Atlas was moving through low-density plasma corridors in the heliosphere. In other words, when the environment was clear and interference was minimal. The distortion got worse. One working theory proposed that the object is employing interferometric dampening. This is a theoretical method in which an object masks its velocity signature by manipulating its own light profile, creating destructive interference that nullifies the Doppler waves reaching the observer. That is not cometary behavior. That is stealth. And it is not passive stealth. Like painting a plane black, it is active. It would require real-time awareness of incoming observation points, a way for the object to sense where it is being watched from and to adapt its output accordingly. This might explain why infrared readings began to drift off baseline as well. Not only was the Doppler signal collapsing in the visual range, but thermal and microwave returns were also dropping in coherence. It was becoming harder to lock onto the object across multiple spectrums. Even ground-penetrating radar arrays that attempted a passive bounce off the solar plasma failed to return usable echoes when Atlas passed through their field of projection. It was as if the object was editing its signature in real time, choosing what to let us see and what to suppress. Such behavior rattled researchers not because it was overtly hostile, but because it was intentional. You don't accidentally suppress a Doppler signal. You do it to hide. And 3I Atlas, in the moment when it moved the fastest, went the most silent. For many astronomers, that silence was more chilling than any flare or fragment, because it wasn't the silence of space. It was the silence of strategy. In the hours that followed the Doppler collapse, analysts began mapping the real space trajectory of 3I Atlas with increasing urgency. They stripped away the confusing light data and relied on pure positional triangulations. Normally, a comet or interstellar object maintains a curved path, a graceful parabola influenced by gravitational pulls, solar pressure, and momentum. But 3I Atlas was doing something else entirely. It was flattening its trajectory. The arc that should have begun to tighten as it accelerated toward the inner solar system was instead beginning to straighten out. The curvature expected from standard Newtonian mechanics was absent. Instead of a parabolic swing around the sun, 3I Atlas was moving along a strange, flattened corridor. It looked almost like it was riding a rail that had been placed across the heliosphere. This raised a disturbing set of possibilities. When comets fall toward the sun and then veer away, their paths are curved because gravity is the driver. But 3I Atlas appeared to resist this curve. It maintained a steady pitch angular but controlled as if it was negotiating the gravitational pull, not succumbing to it. Observatories tracked this over several cycles of solar rotation and saw a consistent trend. The object's orbital path was not tightening into a slingshot. It was flattening into a near-linear motion that ran counter to standard solar orbital mechanics. And then, something else emerged from the navigation data. The angle of this flattening wasn't random. When mapped against the magnetic topography of the solar system, the object's path was aligned with a specific corridor. This corridor had been previously mapped by solar probes as a high-speed solar wind channel, a region where magnetic field lines are sparse and plasma density dips. That meant 3I Atlas wasn't just moving fast. It was choosing its route. Whether by conscious navigation or intrinsic design, the object appeared to be exploiting a low-resistance zone, an invisible highway through space that minimizes drag and magnetic interference. Even most natural solar ejecta particles thrown off by the sun don't utilize these channels so cleanly. They get buffeted and scattered. 3I Atlas, however, stayed in the center of the lane. This suggests an ability to sense the magnetic environment and adjust course to optimize travel. It is the difference between a leaf blowing in the wind and a glider pilot finding a thermal updraft. One is random, the other is exploitation. And as 3I Atlas continued its flattened, silent, and shielded approach, the question shifted from what is it to where is it going next? This specific corridor in the solar system, this high-speed channel, isn't something most comets ever interact with successfully. It is a turbulent, narrow zone where magnetic fields twist and plasma densities fluctuate wildly. To navigate it requires precision timing. It demands a constant awareness of heliospheric conditions and the ability to execute micro-course corrections to remain aligned with the magnetic grain. In nature, comets are like rafts caught in a river. They go where the current takes them. They get buffeted. They drift. But here was 3I Atlas moving through the turbulence with the stability of a submarine. It was flattening its arc, shaving off the curvature, and pushing toward Earth's orbital plane at an unnerving angle of attack. That specific phrase, angle of attack, brought back memories for many in the astronomical community. It recalled the days of Oumuamua, the first interstellar object ever detected passing through our system in 2017. Oumuamua also exhibited non-gravitational acceleration. It also puzzled scientists. But this was fundamentally different. Oumuamua tumbled. Its light curve showed it was flipping end over end. A chaotic, uncontrolled rotation typical of a piece of debris that had been violently ejected from its home star system, 3I Atlas. By contrast, moved with a confidence that was almost architectural in structure. Its rotational axis was locked. Its motion was smooth. One researcher at the European Southern Observatory described the trajectory as rail-like, not because it was a straight line in the literal sense, but because it felt engineered. It looked like something that had planned this path long before it arrived at the edge of our solar system. As the arc flattened further, a new mathematical worry emerged: velocity alignment. In orbital mechanics, the closer an object's path gets to a straight vector, the harder it is to predict where it might shift next. In standard curved orbits, gravity is the dominant force, which helps constrain predictions. We know how gravity pulls, so we know where the rock will go. But in a near-linear path, a path dominated by momentum rather than gravity, minor shifts in thrust have massive implications down the line. A 1-degree change now means a 1,000,000-mile difference next week. And the object was still accelerating. In a traditional comet, the tail flares out and influences the trajectory via outgassing pressure in a somewhat random way. But 3I Atlas had shown no standard outgassing. Its anti-tail, in fact, seemed to be doing the opposite of what a tail should do. Instead of passively trailing behind, it appeared to be pulling backward while the object surged forward. This suggested a possible propulsion dynamic that we rarely see: momentum management. The object was shedding something. Yes, but it wasn't shedding mass to lose weight. It was shedding mass or energy in a way that seemed to stabilize its direction rather than disrupt it. And that direction was inching closer, day by day, to a direct intersection trajectory with Earth. The flattening arc wasn't just a curiosity for the journals. It was a signal. It meant that whatever governed the motion of 3I Atlas was doing more than reacting to solar forces. It was minimizing the curve. It was minimizing deviation. It was flattening its path into something more efficient, more targeted, and more deliberate. That is the kind of movement you don't see in cosmic debris. You only see it in missions. While most eyes remained locked on the flattening arc of the trajectory, a quieter but equally strange phenomenon began emerging in the imaging stacks from Earth's magnetospheric monitoring satellites. It started as a subtle variance in background ion density, recorded by 2 deep space probes designed to watch for solar wind disturbances. These instruments, the ACE and D-SCOVR satellites, weren't designed to track cometary structures. They were meant to study Earth's plasma environment to predict space weather. But what they picked up intersected with something else entirely. It was a pulse. This pulse did not originate from the core of 3I Atlas. It came from its anti-tail, that backward-facing projection. Once believed to be a passive trail of ionized dust and particles, began showing signs of active emission. The emission wasn't continuous like a jet engine, nor was it sporadic like a flare. It was rhythmic. It repeated in an ultra-low frequency range that brushed just beneath the threshold of detection. Yet, once the pattern was isolated from the background noise, it was undeniable. The anti-tail of 3I Atlas was pulsing like a heartbeat. That changed everything. In standard cometary science, anti-tails are typically explained as optical illusions, projection effects created when Earth crosses the comet's orbital plane. We see a sheet of dust edge on, and it looks like a spike pointing toward the sun. It is a trick of perspective. But this anti-tail defied that logic. It wasn't a trick of light. It was emitting its own energy signature, one that cycled in amplitude and direction. The pulses appeared to ripple not outward into space, but inward, as if drawing the surrounding plasma toward the body itself. This wasn't the behavior of a simple solar-wind interaction. It resembled signal compression or even wavefront modulation patterns that, until now, have only been seen in human-made radio transmissions, never in natural celestial bodies. Researchers at NASA's Deep Space Network tried to map the timing of the pulses and quickly realized they weren't random. Each cycle seemed to mirror the velocity of the solar wind. It was a reactive behavior, more akin to sensor feedback than passive diffusion. The anti-tail wasn't just receiving pressure from the sun. It was responding to it. That response was rapid. Within minutes of a solar wind surge, or a microflare from the sun's corona, the anti-tail would compress and release a dampened pulse, as if it were absorbing the momentum and offloading it into calibrated shocks. That dynamic, an object not just pushed by space weather, but reacting to it and counteracting it, was unheard of in astronomy. Then came the next twist. As the anti-tail pulsed, Earth's own magnetometers showed faint but consistent fluctuations across high-latitude stations. These weren't geomagnetic storms. They weren't auroral bursts caused by solar particles hitting the poles. They were coherent field distortions, subtly altering Earth's ionospheric layers in perfect synchrony with the anti-tail pulses. It was as if the tail was emitting a directed feedback loop targeting Earth's upper atmosphere from tens of millions of miles away. The implications were difficult to process. If the anti-tail was broadcasting, whether intentionally or not, it was doing so in a frequency that propagated through the solar plasma, bent around magnetic field lines, and landed directly on Earth's electromagnetic sheath. And this wasn't a one-off anomaly. It was repeatable. Every pulse correlated with a distortion. Every emission left an echo in Earth's space weather shell. That raised the possibility no one wanted to entertain aloud. Was the anti-tail a communication structure, or worse, a navigation tool? If 3I Atlas was using its anti-tail not to shed particles, but to probe, to map, and respond to external fields, then the object was not behaving like a comet at all. It was acting like a vessel. It was maintaining course correction through real-time environmental feedback. Its anti-tail was functioning like a rudder one that didn't move physically, but electronically, it was calibrating through pulses, steering by distortions, and communicating with the space around it. And all of this became clearer as the object approached the boundary of Earth's orbital plane. The pulse response wasn't diminishing. It was amplifying. It was as if the object knew it was entering the final corridor, and it was preparing for something ahead. As ground-based observatories continued tracking the rapid acceleration, a quieter revelation was unfolding above Earth's orbital path, something subtle yet deeply uncharacteristic for any known comet. It emerged in data stitched together from the Solar Dynamics Observatory and a series of low-frequency plasma scans collected across 2 hemispheres. The object wasn't just reacting to solar wind, it was actively avoiding it. The realization began with an analysis of bow-shock angles. Normally, as a comet or asteroid enters regions of denser solar radiation, the surrounding plasma builds pressure, forming a shockwave boundary similar to the curved wave in front of a boat cutting through water. With 3I Atlas, that arc was missing. Or rather, it was misshapen. The expected curvature didn't match its position or velocity. Instead, the boundary was tilted. It bent away from direct pressure in ways that should have been impossible at this distance from the sun. At first, it looked like a measurement glitch. Then came the second anomaly, angular deviation. 3I Atlas had begun making micro-adjustments in its orientation. These weren't random spins. They were direct responses to minor fluctuations in the solar wind stream. These were course corrections, subtle shifts measured in arc seconds, but consistently timed within minutes of solar ejection events. It was behaving like a drone avoiding turbulence. And there was more. Each shift was accompanied by a measurable drop in reflectivity across its sunward surface. Instruments reading albedo brightness and radiative return noticed that the object became temporarily dimmer whenever it reoriented. This wasn't due to a coating of dark particles. It wasn't due to a loss of material. It was as if the object was modulating its exposure, employing adaptive shielding. It appeared to be absorbing less light and energy precisely when the pressure spiked. That led to the third layer of the pattern geometry manipulation. High-resolution imagery captured a transient distortion around the object, not in the body itself, but in the surrounding dust and plasma cloud. It formed a cone. This cone deflected incoming solar ions, not just passively, but preemptively. The object's surrounding field likely composed of charged debris and gas bent to match the angle of incoming energy. It didn't push away from the sun directly, it pushed along the path of least resistance. This meant that 3I Atlas was navigating like a vessel with vector awareness. It understood where the energy was coming from and adjusted to reduce impact. That isn't comet behavior. That is tactical behavior. The deeper analysts looked, the clearer it became. The solar wind avoidance was not a single event. It was a sustained sequence, over the course of several hours. The comet realigned its heading not to gain speed, but to avoid direct collision with denser solar wind packets, regions where particles become compact and chaotic, capable of destabilizing fragile or synthetic structures in space. The changes were most pronounced when a coronal hole opened in the sun's atmosphere and released a surge of fast-moving ions, while other comets would have been bombarded, forced to react after impact. 3I Atlas moved before contact. The trajectory veered just slightly fractions of a degree, but enough to avoid the core of the wind stream. This timing implies something profound. It couldn't be random. It suggests the object was either observing the solar field through some embedded detection system, or it had a memory of similar interactions in the past. If the object was capable of recognizing the patterns of solar activity and adapting before the wave reached it, then it possessed something no comet has ever had. It had anticipation, and anticipation hints at a layer of complexity far beyond even our most advanced asteroid deflection systems. This wasn't shielding. It wasn't brute force resistance. It was evasive maneuvering. The question that now burned through every observatory and data center was this: if 3I Atlas could avoid the sun's pressure with such calculated precision, what else was it capable of avoiding? And more importantly, what was it trying to reach by doing so? For most comets, the story told by their tail is straightforward. It is a simple narrative of physics. Gas and dust stream away from the sun, stretched into space by the relentless pressure of solar radiation and the bombardment of charged particles. It is a messy, turbulent exhaust plume. But with 3I Atlas, the story unfolding behind it defied every expectation of cometary mechanics. What formed in its wake wasn't just a tail, it was a shadow. And it was not a shadow cast by the blocking of light, but by the blocking of plasma. The discovery began just hours after the object's evasive maneuvers against the solar wind became evident. Instruments aboard Earth-orbiting observatories, specifically designed to monitor space weather, started noticing unusual behavior in the heliospheric environment directly behind the object. To understand why this is strange, we must understand the medium of space. It is not empty. It is filled with the solar wind, a constant, flowing river of ions and electrons moving at supersonic speeds. Normally, when a comet moves through this river, its tail disrupts the flow for a short distance, creating a wake of turbulence that eventually mixes back into the solar stream. just like the wake of a boat dissolves into the ocean. But behind 3I Atlas, the disruption wasn't dissolving. Instead, it was deepening. A long, coherent corridor of reduced particle density extended across space like a vacuum channel. As the object accelerated toward Earth, this corridor stretched even further, maintaining an eerie symmetry and a sharp boundary definition that no natural debris field should possess. Nature tends toward chaos and mixing. This structure tended toward order and separation. Scientists dubbed it a plasma shadow. This is a term not formally used in astrophysics until now, largely because such a phenomenon had never been observed on this scale. At first, the data teams assumed this was an instrumental artifact, perhaps an optical illusion caused by scattering, or a fluke in solar activity occurring coincidentally behind the object. But measurements from independent platforms showed consistent drops in charged particle counts within that specific zone. Detectors aboard NASA's STEREO spacecraft, the Solar Terrestrial Relations Observatory, noted that solar ions were not just passing through the region, they were being rerouted. The telemetry suggested that the charged particles of the solar wind were being deflected sideways, flowing around the region behind 3I Atlas rather than passing through it. That distinction is critical. That wasn't passive shadowing, like a rock blocking the wind. That was field-level manipulation. The structure wasn't merely an absence of particles. It was the presence of something else, something acting like a shield, holding the solar wind at bay to create a straight, artificially clean void. And what made it more mysterious was that the tail wasn't even active in a traditional sense. There were no visible gas jets spewing material. There were no consistent ejection trails. There were no signs of fragmentation that could explain why the solar wind was being pushed aside. So, what was forming this corridor? Some theoretical physicists proposed that the anti-tail, previously thought to be a simple geometric phenomenon or a dust spike, was actually behaving like a charged sheath. The theory suggests it was repelling ionized matter on a constant electrostatic frequency, effectively creating a force field that pushed the solar wind outward. Others suggested that the object might be enveloped in a self-sustaining plasma cocoon, maintaining a balance between its rapid forward motion and the rear pressure of the solar environment by ejecting tiny, undetectable packets of magnetic flux, whatever the mechanism. One thing was now indisputable. Particles were afraid of following it. The plasma behind 3I Atlas was behaving like water flowing around an invisible, streamlined fin, even when solar activity spiked, sending waves of higher pressure through the system. The corridor held its shape. It did not fragment. It did not fill with gas. It did not flutter like a normal tail would under stress. It held like a rigid tunnel. Further analysis brought another unsettling detail. Within this vacuum corridor, background radiation levels remained stable, but electromagnetic interference surged on fringe frequencies. This meant that the space wasn't just empty, it was electrically active. Signals sent across this region returned distorted, phase-shifted, and garbled. It was as if the region behind the comet was not just clean, but curved bending waveforms and interfering with telemetry. To scientists watching in silence, this was no longer looking like a comet tail. It was beginning to resemble a trail of influence, a command trail, perhaps, or the waste heat of an internal energy field unknown to our current models. The implications were dizzying. If 3I Atlas could sculpt the space behind it, clearing out the solar wind, shaping radiation corridors, and distorting signals, it meant one thing. It was not just protecting itself from what was ahead. It was effectively clearing a path. In naval warfare, a minesweeper clears a channel for the ships that follow. In aerodynamics, A lead truck breaks the wind to create a slipstream for the convoy. If 3I Atlas is creating a protected vacuum channel behind it, the question becomes, is it clearing a path for something that is following, and whatever that something is, it has not yet revealed itself. As 3I Atlas pushed further toward Earth at unprecedented speeds, the focus of the investigation shifted from the object itself to an invisible structure that stretches out behind our own planet, the magnetotail. Earth is protected by a magnetic field, and the solar wind stretches this field out on the night side of our planet, creating a long, trailing extension known as the magnetotail. Imagine it like a long windsock trailing behind a pole in a stiff breeze. Under normal conditions, it behaves predictably. It fluctuates gently as space weather shifts, flapping in the solar wind, but it never breaks its fundamental form. That was until the morning of December 16th. At first, the change was subtle, a narrowing in the rear length of Earth's magnetotail. This kind of compression has occurred during massive solar storms in the past. But something about this specific compression seemed wrong to the analysts. It wasn't caused by high-speed solar particles slamming into the front of the magnetosphere and squeezing it. Instead, the compression was happening in the absence of such pressure. The source of the stress seemed to be coming from behind the planet, not from the direction of the sun. The European space agencies cluster two spacecraft stationed in the far reaches of the magnetotail to study plasma physics began returning telemetry that didn't line up with any previously logged pattern. The tail's alignment had shifted. Normally, the tail wavers slightly, pushed by gusts of solar wind or ripples in the interplanetary magnetic field. But on this day, it snapped into an unnatural shape. It formed a tight, constricted bow that bent as though it were being pulled from behind by an invisible tether. Something was tugging on the back of Earth's magnetic signature, and when they traced the vector of that tug, it aligned precisely with the position of 3I Atlas. What followed was even stranger. For the first time in decades of satellite observation, scientists detected waveform interference not just in the field strength of the magnetotail, but in its oscillation frequency. The tail began pulsing. It was beating rhythmically, as if responding to a distant beacon or a tuning fork. This was not a solar flare. Solar flares are broad-spectrum noise. They scream across all frequencies. This was a specific, resonant hum. This was interaction. The direction of the pull lined up almost exactly with the trajectory of 3I Atlas as it approached our orbital plane, even though the object was still millions of kilometers away. The fields were already reacting. This meant that either the comet was emitting some unknown energy signature that traveled ahead of it at the speed of light, or the vacuum void it carved behind itself was somehow coupling with Earth's magnetotail. In either case, the implications were staggering. Imagine Earth's magnetic shield as a long ribbon trailing behind a boat. Normally, it dances gently in the current, but now, it felt as if something from across the ocean had snagged the end of the ribbon and was beginning to reel it in. The effects were not limited to space. Atmospheric monitoring stations across the northern hemisphere began reporting minor but inexplicable auroral anomalies. Brief flashes of color, greens and violets, appeared in regions where they shouldn't, at latitudes too far south for normal auroras. The ionosphere, Earth's protective upper shell of charged particles, began fluctuating at altitudes inconsistent with any solar triggers. Radio waves reflected strangely off the upper atmosphere. Global Positioning System satellites saw minor signal losses and timing drifts. Cosmic ray detectors on the ground pinged with rare, directional bursts. Everything pointed to the same conclusion: Earth's magnetotail was being interfered with. But it wasn't being battered by a storm, it was being manipulated. The interference was precise, it was patterned. That distinction terrified physicists more than chaos ever could. Because patterns require intention, the anti-tail of 3I Atlas. Once considered a mere curiosity or an optical phenomenon formed by its angle and path, was now acting more like an antenna. The further the object accelerated, the more the interference escalated. It began synchronizing, almost like a frequency handshake between the object and Earth. No one in the control rooms was ready to say the word communication. That implies language. And we had no evidence of that. But no one could ignore the physics. Earth's electromagnetic body was now entangled in a one-way interaction with a celestial visitor. We were no longer just watching it approach, we were feeling it. And as the distance closed, we barely understood the scale of the connection forming in the dark. What came next would only deepen that entanglement, because as the magnetotail bent and trembled under the invisible influence of 3I Atlas, something else began to shift. The disturbance was no longer confined to the vacuum of space. It had descended. It was now happening in Earth's atmosphere itself. Just after the magnetotail began showing signs of abnormal tension, a new class of anomalies emerged. These were not detected by deep space telescopes, but by atmospheric sensors in human eyes. Over the vast, empty stretch of the Pacific Ocean, a region where electromagnetic silence is typically maintained, a series of localized, high-altitude electrical disturbances suddenly appeared. These were not lightning storms. They were not upper atmosphere auroras caused by solar wind. What they were defied every known category of atmospheric science. At first, they appeared as faint, glowing pulses, soft, spherical emissions hovering high above the troposphere. Sitting almost at the ragged edge of space, commercial pilots flying the heavy-haul routes from Tokyo to San Francisco noticed the flickers first. In their flight logs, they reported them as ghost lights, dim, persistent flashes that did not move or branch like jagged lightning. Instead, they swelled and contracted, pulsing like breathing orbs of plasma. Air traffic controllers flagged the events and began redirecting flight paths. This was done not out of panic, but because of a functional necessity. An unexplained radio blackout zone had begun to widen over the central Pacific. Radio towers on remote island chains like Guam, Kiribati, and Midway began experiencing signal distortion. This wasn't static. It followed a strange, oscillating rhythm, almost like an encoded frequency modulating directly in the upper ionosphere. At sea level, the world remained quiet. The ocean was calm, but in the stratosphere, strange clouds began to form. They were not made of water vapor. They were not made of ice crystals. And they were not volcanic dust. These were electrostatic aggregations, visually similar to noctilucent clouds, those rare, shining clouds seen at twilight, but far denser and far more uniform. Satellite thermal imaging scans of these clouds showed no heat emission, which is physically baffling for a cloud formation. Yet, LiDAR scans, which use laser pulses to map structure, suggested they had an internal architecture. They contained coils and filaments, appearing like circuits woven into skyborne lattices. And this is when the scientific community could no longer deny the pattern. When they overlaid the map of these atmospheric events with the orbital trajectory of the object, the correlation was absolute. Every single charge event was located directly underneath the vector line of 3I Atlas's acceleration path. It wasn't random. The timing was synchronized. 3I Atlas had not yet entered Earth orbit. It hadn't even crossed into the geostationary belt where our satellites live. but something about its proximity, and more specifically, something about the orientation of its anti-tail, was creating electromagnetic responses in Earth's upper atmosphere that were not chaotic. They were geometric. Across international observatories, a consensus began to form. It was quiet at first, whispered in private encrypted messages between research teams, not yet ready for public scrutiny. The theory was this: these events weren't just reactions, they were preconditions. In other words, Earth's upper atmospheric layers were preparing. They were not breaking, they were not collapsing, they were reconfiguring. It looked as if the atmosphere was being formatted, adjusted, and tuned to a specific resonance. And then came the discharges. Over the course of 10 minutes, instruments on board the International Space Station, passing over the Pacific Theater, detected 4 distinct bursts of charged particles. But these particles were not raining down from the sun, as they typically do during a geomagnetic storm. They were rising. The particles were streaming from the Earth into space. This reversal was deeply unsettling to the physicists monitoring the feed. It was as though something was pulling the energy up. It wasn't extracting it in a destructive way. Like a siphon, it appeared to be sampling it, drawing the energy in through a narrow, vertical corridor that remained invisible to the naked eye. Simultaneously, radio operators in the South Pacific archipelagos began hearing strange static tones in the amplitude modulation, or AM, band. These tones were structured, they were tonal, and they repeated every 30 seconds like clockwork. The sounds were not artifacts of thunderstorms. They matched nothing in the library of known weather patterns or solar interference. They were being emitted, or at the very least, facilitated by the atmosphere itself, acting as a planetary-scale transmitter. It no longer made sense to speak of Earth systems as isolated. They were being included. They were being drawn into a process whose logic could not be denied, one that had already started before humans even recognized it was happening. The atmospheric charge events over the Pacific were just the first signs, but they wouldn't remain localized. Just hours after those quiet, geometric pulses began appearing over the open ocean. They began appearing on land. Sensors registered them over mountain ranges, over deserts, and eventually over densely populated cities. Each event followed the same rules, and those rules pointed to something that Earth had never encountered before, something that didn't need to land to interact, something that used fields, not fire. For weeks, scientists had tried to explain the strange, forward-facing trail extending from 3I Atlas. Unlike typical comet tails that stream behind the object due to solar wind pressure, this one pointed toward Earth. It refused to behave like any known ion tail. It didn't diffuse into space. It didn't fragment into wisps. It didn't even glow consistently. It pulsed with mathematical regularity. And on the morning of December 16th, a theory began to circulate that would fundamentally change the way we understood this object. It wasn't a tail, it was a gate. This idea didn't come from fringe thinkers or internet forums. It came from within a small, international consortium of astrophysicists who had been quietly collaborating since the object's unexpected acceleration event. After running weeks of simulations using particle behavior data, polarization shifts, and Doppler distortions, they realized the physics of the so-called anti-tail were wrong. It was not ejecting material, it was aligning vectors. Specifically, it was aligning directional field lines that responded not to gravitational forces, but to inertial opposition. In simple terms, it wasn't a stream of gas. It was a channel. It was a corridor, a tunnel-like structure that didn't push matter out, but instead bent surrounding space inward, and the direction it bent was always, unerringly, toward Earth. The strange, stabilized field lines forming in the ionosphere over the Pacific began to match the very same geometry found in the core of the anti-tail. It wasn't a coincidence. They were mirror images, one in the sky, the other in deep space, linked by orientation, rotation speed, and alignment with Earth's magnetic north. When researchers overlaid the data, the patterns formed what looked eerily similar to a bridge, a mathematically symmetrical connection stretching across hundreds of thousands of miles. The consistency suggested a design principle. It was not accidental. It was not naturally chaotic. It was deliberate. This forced researchers to re-examine the function of tails entirely. If the object wasn't simply moving through space, but manipulating the medium of space itself, then it wasn't a comet in the traditional sense. It was an environmental manipulator, a body capable of rerouting energy fields, not unlike how humans reroute electrical currents using copper wires and semiconductors. But this thing wasn't using wires. It was using space itself as the conductor. The term vector gate began to appear in internal reports. It was not a headline for the public. It was shorthand among top-level discussions at the Jet Propulsion Laboratory, the European Space Agency, and a few defense-aligned observatories. It was their way of describing the observed phenomenon, a fixed, narrow spatial conduit stretching between 3I Atlas and Earth. It was held open not by solid matter, but by inertial resonance and electromagnetic matching. It wasn't stable in the way a wormhole might be described in science fiction. It wasn't glowing or spinning, but it was structurally stable, as evidenced by the repeating fields appearing over Earth. And that made it functional, not theoretical, not metaphysical, functional. And then came the final confirmation, something no one expected: the neutral particle detector on the Parker Solar Probe, which is currently operating near the Sun and had been repositioned days earlier to monitor the event, recorded a stream of neutrinos. Neutrinos are ghostly particles that typically pass through everything, but the probe detected a stream of them traveling against the solar wind. That shouldn't have been possible. Yet, the trajectory of this neutrino stream lined up perfectly with the orientation of the anti-tail. Something was moving through the gate. It wasn't debris. It wasn't hazardous radiation. It was structured, pulse-based, and repeating. Whatever it was, it wasn't traveling at random. It was navigating the corridor with purpose. And that raised the final, inevitable question: was this a message? Was it a test? Or was something or someone already using the gate? The anti-tail was never meant to be looked at from a distance as a decoration. It was never just a visual marker or leftover dust. It was the key to the entire behavior of 3I Atlas. And now, it had locked on to Earth. So now, we are left with something no telescope was built to explain. We have an object that doesn't behave like a comet. We have a structure that doesn't resemble any known spacecraft. We have a pathway that forms without propulsion. And we have a silence unshakable and total that only deepens the mystery. On the morning of December 16th, 3I Atlas accelerated by a factor of 33. It did not do so randomly. It did not do so chaotically. It moved in a direct, unbroken alignment with Earth, and at the exact same moment, its forward-facing anti-tail, which we now understand may be anything but a tail locked into orientation with a newly forming pattern in our sky. And still, no agency has offered a complete explanation. They call it a natural anomaly. They describe the acceleration as an unmodeled outburst. But the patterns are too clean. The resonance is too precise. The symmetry is too perfect to ignore. If 3I Atlas is artificial, it is not a message we are hearing. It is a function we are witnessing. It didn't shout. It didn't announce its arrival with radio signals. It didn't change direction erratically. Instead, it moved with quiet purpose. And what it left behind wasn't debris. It was geometry. It is a kind of invisible math, unfolding quietly across the solar system, as if it knows exactly where it is going and why. So, what do we do with that? What do we say when something this large, this precise, and this focus drifts silently toward our planet, not to strike, not to destroy, but to connect? We keep watching. We keep listening, because sometimes the most intelligent thing an object can do is say nothing at all.